a to the k, b to the n minus k. And we're going to prove, oh, 2 zeros in prove, that's useful. Okay. A plus b to the n plus 1 equals the sum from k equals 0 to n plus 1 of n plus 1 choose k, a to the k, b to the n plus 1 minus k. Okay, you see where our little lemma might come in handy here, because we have to get this, and we're assuming that. All right, now, like you often have to do when you're proving something, you have to make a choice. You're going to have to decide which side of this equation are you going to start with? Are you going to start with this one and work toward that? Or are you going to start with this one and work toward that? Now, in this case, and it's really not, I'm not really sure how to give you some intuition for this, except to say if you play around with it for a little bit, you will see that this becomes rapidly unpleasant. Okay, because what would you do with this? You would take this and you would then split off the n plus first term, right? And then you would put that in, but the problem is that when you split off the term, you can't just use the inductive step. Does everybody see this? If you were to start with this, what would be the problem with you? So normally, what in the proofs you've done using sums, what have you done, right? You've split off that last term, and then you've taken this one, and you've just stuck it in there. Why is that not really possible in this case, or why is it difficult in this case?
If you break off the first term, there's still the n plus 1.
Yeah, you got an n plus 1 in here, you got something different in there, so you're not going to be able to just use that. Okay, so that's why you should be scared off by starting with the right-hand side. And, you know, again, this is just instincts that you develop proving a lot of things. And at any rate, if I had just seen this for the first time, I might have started that way too. And so I thought about what if I did start that way, knowing that it's a bad idea, and why would you very quickly realize it's a bad idea, and that's it, okay? So the more that you get choices, right? Choice is good, right? Well, except your life was really easy when you had to solve a problem, there was only one way to do it, right? Okay? The more you have choices, and you will have more and more and more, the more you have to make a decision about what you're going to do, how are you going to proceed, what theorem are you going to use. Okay, and so in this case, and I encourage you to think about doing it backwards. It's possible. Basically, you can just run backwards what we did here, okay? But it means, you know, using that backwards, breaking it up, it's just really, there's no instinct for what to do. Okay, so we're going to actually start with this side, and we're going to wind up with that side. Okay, we're going to need lots of space for this. So we're going to start with a plus b to the n plus 1. And you'll very quickly see why this is a little quicker, because you immediately can use your inductive hypothesis when you start on the left side. Okay? Because how would you break this up? In a normal inductive proof involving a power, which you've already done some in your homework, right? Yeah, break off one of the terms. Okay, so this is a plus b to the n times a plus b. Right? And now you can immediately take the left-hand side and put it in there. So now you're done with the inductive hypothesis. No playing around or anything, right? Now that it's in there, it's just a matter of working with it until you get this. Okay. So this is the inductive hypothesis, right? Let's put that thing in. So the sum from k equals 0 to n of n choose k, a to the k, b to the n minus k times a plus b easy so far, right? But things are not going to stay so easy for long. Okay, so now what we're going to do is we're going to distribute. Okay, now just be careful about what we're doing here. We're taking this whole sum and we're multiplying it by this, and then we're adding to that the whole sum multiplied by that. This is just a number, okay, when we distribute this. So just writing out a couple extra steps here just to be sure you see what's going on. The sum from k equals 0 to n of n choose k, and maybe I'll just put my a out in the front here, okay? N choose k, a to the k, b to the n minus k, plus b times the sum from k equals 0 to n choose k, a to the k, b to the n minus k. And now we're distributing again. So we're going to distribute this a all the way across here, and then b all the way across there. So let's think about this. Each term is just a product of these things. So the a gets absorbed in this how? Gets sucked into that power, right? Okay? So this is going to be the sum from k equals 0 to n of n choose k, a to the k plus 1, b to the n minus k, plus sum from k equals 0 to n choose k, a to the k, b to the n plus 1 minus k. Now, of course, you'd like to combine these, but you can't do it because these terms are not the same as those terms for any particular k. So here's where trickery starts to happen. But let's look. Some things are looking good. Well, one thing is looking good. What's the one thing that's looking good?
B to the n plus 1 minus k.
That is looking good, okay? That's the only thing, but that looks good, right? Because that's what's supposed to be here. And so we can sort of latch onto that as what we want to go for. And you see, this isn't right.
So we want to fix it.
So we want to fix it. Now, we're going to fix this using an index shift. Okay, so this should remind you of change of variables back in calculus, okay, when you were doing integral. And when you do change of variables, you do, or otherwise known as substitution, but change of variables is really a better thing, right? What did you have to do? Well, you had to do your substitution inside, but you also had to figure out your new limits of integration, right? When you're, right, you had a new variable. The new variable usually didn't go from the same place to the same place, right? It was changed. Well, so in this, the same thing is going to happen. We want to do a little index shift, right? And here's the idea. Let's suppose we replace, and there's a more formal way to do it, but k by k minus 1. Now, why can I do this? Well, why could you do these sorts of things with integration? Because you had what's known as a dummy variable, right? And you could call that whatever you wanted to. And so, likewise, this k is kind of a dummy variable in the sense that all it does is it tells you what numbers to plug in. Okay? And so what we're going to do is we're going to shift this whole thing, and we're going to get a new sum which changes all these things to what we want. But remember, these things are just numbers. Everything involving k is just numbers. And so as long as the numbers are the same, then we're okay, right? For example, I could change the k without doing anything. I could change the k to a w and get the sum from w equals 0 to n of n choose w, a to the w plus 1, b to the n minus w, and that would be the same thing, right? That's the dummy variable idea. It doesn't matter what I call it. Okay, so the idea is that I'm going to replace k by k minus 1 and shift this entire thing. So let's just go through, and we're just going to work on this one, right? So let's suppose I did that. So k goes from where to where? Here. K goes from 0 to n. So if I want to get the same numbers out of k minus 1, what does k minus 1 have to go? From where to where? Has to go from 1 to n. K has to go, right? From 1 to n plus 1. Now let's just check that, right? Because if k is going from 1 to n plus 1, where does k minus 1 go? From 0 to n, which is exactly where I want it to go. Okay, now we'll just do this and then go back and check and make sure we're getting the same numbers in the sum. Okay, so now let's look at this. Okay, so I'm replacing k by k minus 1. So this should be n k minus 1, right? And here I have a to the k plus 1, but I'm replacing k by k minus 1. So that's just a to the k. And now I'm replacing k by k minus 1. So I get b to the n minus k minus 1. Things are looking better. What has now been fixed by this? What's that actually equal to? N plus 1 minus k. So we've now fixed this. Now let's just make sure, right? Does this count through the same thing? So let's just look at the endpoints, for example, because it's just counting by 1, okay? So where does this start? This starts at n choose 0, a to the 1, b to the n. Where does this start? A to the 1. Oh, sorry. N choose 0. And actually, you just need to check where it starts. As long as it starts at the same place and the number of terms is the same, then it has to end in the same place because they're both counting by 1. So we'll just check the beginning, right? And so this is now a to the 1, b to the n. So this sum involves the exact same numbers as the previous sum. Now, if you don't like the little mental stuff there, you can always let, let's see, m equal, I always have to think about this a little bit. You can also let m be equal to k plus 1, and then replace k. Right, make the replacements in here everywhere, okay? So that would give us the sum, right? So this is from m equal k, m equal 1. I don't like doing it this way, but anyway, it's an alternative. M equal 1 to n plus 1. N choose m minus 1. A to the m, b to the n minus m minus 1. So then you see that's the same thing we did there, and then you can just replace m by k. I mean, the key is to figuring out what the substitution is, as always, right? But when you do this, because it's easy to make a mistake, when you're done, just check. Just check one term at one end or the other. If you're just doing a basic shift, just check the first term. If it's the same, if it's the exact same number, when all the smoke is cleared, then you've done it right. If it's a different number, then you haven't done it right. So what does this now become? This now becomes the sum from k equal 1 to n plus 1 of n choose k minus 1, a to the k, b to the n plus 1 minus k, plus the sum from k equal 0 to n of n, so we're looking at now this term here. N choose k, a to the k, b to the n plus 1 minus k. Okay, things are looking really good because these are now what they're supposed to be, right? Because remember, we're after this. So these terms are correct. And also, what is the sum of those two things? The sum of those two things is this guy. So yeah, we're done, right? Well, not quite. We would like to combine these two guys together, right? But what's going to cause problems with combining? There's one more thing to fix. Yeah, the limits of the summation are different. Okay, well that's really easy to fix. Because what we're going to do is we're going to separate off the n plus first term of this, and we're going to separate off the 0th term of that. And then we'll have the what's left will have the same ranges, and then we'll combine the whole thing back together. Okay?